The coldest place in space ever found is not a frozen planet, nor a distant ice-covered moon. It is something stranger, something that defies ordinary intuition. A region where temperatures drop below the already glacial background of the universe itself, plunging close to absolute zero. At such extremes, atoms barely move, and thermal energy, the fundamental vibration of matter, nearly vanishes. In this condition, reality itself seems to stall, as if the very machinery of the cosmos were hesitating. It is colder than anything on Earth, colder than the vacuum between stars, colder than liquid helium or nitrogen can ever reach in a laboratory, unless forced there by human ingenuity. Absolute zero. 273.15 degrees Celsius, or 0 Kelvin, is the theoretical floor of all temperature. It is the point at which molecular motion halts, entropy reaches its lowest possible value, and time itself seems bound to silence. This limit cannot be reached in practice, yet nature brings us unnervingly close. In the recesses of interstellar space, the physics of expansion, radiation, and isolation combine to create conditions so extreme that even the laboratory's most advanced magnetic traps struggle to match them. What exists there is not simply an absence of heat, but an altered regime of matter. To encounter such places, even if only through telescopes and detectors, is to witness the universe revealing something about its inner architecture. The cold is not a void, it is a kind of presence, an active force that slows the dance of molecules, erases the noise of energy, and uncovers hidden forms of order. When atoms move almost not at all, they stop behaving like individuals. They merge into unified entities, following laws of quantum mechanics that are invisible at ordinary scales. Coldness, in this sense, is not emptiness, but a pathway into a new kind of reality, a psychological and physical liminality where the expected rules weaken. This is why the coldest place in space is not only an astrophysical curiosity, but also a psychological riddle. Human beings are warm-blooded creatures, neurologically tuned to narrow temperature ranges where survival feels safe. Cold is coded in the brain as a primal threat, a sensation that can trigger pain fibers, stress responses, and even hallucinations. Prolonged exposure to low temperatures can distort time perception, impair decision-making, and provoke states of altered consciousness. Mountaineers describe a creeping calm before hypothermia, an almost euphoric clarity as their bodies shut down. In ancient myth, cultures often imagined frozen realms as domains of gods or demons, not because they had measured the thermodynamics of space, but because cold, even in moderation, strips away ordinary sensation and replaces it with something uncanny. The Boomerang Nebula, measured at just 1 degree above absolute zero, is one such place. It lies in the constellation Centaurus, about 5,000 light-years away, and it challenges every expectation of how cold the cosmos can become. Its temperature is lower than the cosmic microwave background, the universal radiation that pervades space and keeps the average temperature of the universe at a steady 2.7 Kelvin. That any object could cool beneath this baseline seems paradoxical, as if it were slipping outside the grasp of universal law. Yet astrophysicists have measured it, verified it, and confirmed its reality. Extreme cold in space is not simply a backdrop for starlight. It shapes the behavior of gases, dust, and radiation. It determines how clouds of matter collapse into stars, how energy escapes into the void, and how chemistry takes place in conditions that appear barren. Molecules like hydrogen and carbon monoxide cling together in these frozen regions, forming ices that later seed planetary systems. Life as we know it owes something to the architecture built by cold, and yet we remain instinctively alien to it. For neuroscience, the fascination is parallel. Cold is not merely sensed through the skin, it penetrates the deepest circuits of the brain. Thermoreceptors in the body trigger neural patterns that signal threat, safety, or illusion. Experiments with cryogenic cooling of neural tissue reveal how electrical activity slows and reorganizes under cold stress, sometimes preserving functions in ways warmth cannot. At extreme lows, memory, perception, and cognition can all shift into strange configurations, echoing the illusions of cold environments in nature. This interplay between cosmic and psychological cold blurs into a metaphor. To study one is to glimpse the other. The universe is a laboratory beyond our reach, but its lessons fall back onto Earth, where scientists replicate its extremes. Laser cooling, magnetic traps, and cryostats are all attempts to mimic cosmic temperatures, creating states of matter like Bose-Einstein condensates that behave in ways more wave than particle. These are not just curiosities, they hint at applications in quantum computing, superconductivity, and the hidden powers of matter at the lowest limits of energy. If there is a reason to peer into the universe's coldest corners, it is because they remind us that reality is layered with thresholds. Beneath the warmth of stars and the moderate climate of planets lies a deeper order, one that seems indifferent to life yet strangely informative about its possibilities. Cold reveals fragility, but also coherence. It slows chaos and uncovers structure. What seems dead may, under a different lens, be charged with unseen potential. The coldest place in space is not only a fact of astrophysics, it is an invitation to look closer, to recognize that the universe holds secrets where energy almost disappears. To follow those secrets is to glimpse the frontier of science and the edge of human understanding. Temperature, when reduced to its most rigorous definition, is not simply a measure of how hot or cold something feels to human skin. It is a quantification of motion itself. The kinetic energy of atoms and molecules vibrating, colliding, and dispersing their energy into surrounding space. Every trembling bond, every restless particle, contributes to what we call heat. To lower temperature is to suppress this motion, to reduce the agitation of matter until its constituent particles move with exquisite slowness. When that motion halts completely, the universe touches the unreachable limit, absolute zero. The scale that defines this boundary was first proposed by William Thomson, later known as Lord Kelvin, in the 19th century. His insight was that temperature could be reframed not relative to water's freezing or boiling points, but relative to an absolute state of energy. At 0 Kelvin, 273.15 degrees Celsius, motion ceases. Entropy, the dispersal of energy across possible states, reaches its minimal value. This condition is not simply a numerical point. It is a theoretical horizon beyond which no physical system can be driven. The second law of thermodynamics asserts that absolute zero can never be achieved through any finite number of steps. One may approach it asymptotically, but never arrive. This impossibility has not deterred generations of scientists from inching ever closer. Each refinement in cooling techniques exposes new subtleties in the behavior of matter. Superconductivity, discovered in 1911 by Heike Kamerlingh-Onnes while experimenting with liquid helium, was the first dramatic illustration. As mercury was cooled below a critical temperature, it lost all electrical resistance. Current flowed indefinitely without degradation, defying the expectations of classical physics. Later, experiments revealed superfluidity. Helium cooled to below 2.17 Kelvin could climb the walls of its container, flowing without viscosity. These phenomena demonstrated that near-zero temperatures unlock hidden phases of matter. Not exotic exceptions, but lawful consequences of quantum mechanics revealed only under extreme suppression of energy. The human nervous system interprets cold through thermoreceptors distributed in the skin and deeper tissues. Ion channels, such as TRPM8, respond to drops in temperature by opening and triggering electrical impulses that the brain decodes as cold sensation. This neural machinery is not linear. Beyond certain thresholds, responses become paradoxical. Pain and numbness can coexist. Perceptions of burning or stinging may emerge in the absence of actual tissue damage, illustrating that cold is as much a construct of the mind as a property of matter. Hypothermia intensifies these illusions, leading to disorientation, memory lapses, and, in advanced stages, the stripping away of survival instincts. Climbers caught on Everest recount removing their gloves or clothing under the delusion of heat, a phenomenon termed paradoxical undressing. Cold distorts the very circuitry that signals danger, creating states in which the boundary between internal truth and external condition is blurred. Absolute zero, while unattainable, provides a conceptual anchor for both physics and psychology. For physicists, it defines the point where classical descriptions of motion collapse into quantum ground states, where particles are governed by probability waves rather than mechanical trajectories. For psychologists and neuroscientists, it serves as a metaphor for the cessation of human warmth, the terminal silence of nerve impulses, and the fragile dependency of consciousness on narrow thermal margins. The two domains mirror one another. Just as matter reorganizes under extreme cold, so does the human mind. Laboratory advances illustrate how close controlled environments can come to that limit. Laser cooling, pioneered in the 1980s, exploits the Doppler effect. Atoms moving toward a tuned beam of light absorb photons and slow, while those moving away do not. Repeated across multiple axes, this optical molasses can bring atoms to microkelvin temperatures. Magnetic and evaporative cooling extend the process further, allowing particles to settle into billionths of a Kelvin. These engineered states, colder than interstellar space, are not curiosities of physics alone. They provide the raw material for technological revolutions. Bose-Einstein condensates, first observed in 1995, demonstrate that matter at such extremes behaves as a single quantum wave function, erasing individuality in favor of collective order. The cold, then, is not passive absence. It is an active frontier where physics discloses patterns invisible under ordinary conditions. Yet, this frontier exerts a psychological pull as well. Human cultures have long projected meanings onto the experience of cold, embedding it in ritual, mythology, and ascetic practice. The Norse imagined Niflheim, a world of ice and mist that coexisted with realms of fire, a cosmological balance. In Japanese ascetic traditions, practitioners stand beneath freezing waterfalls, pursuing clarity through bodily shock. Siberian shamans sought altered consciousness by enduring the cold, interpreting its sensory disruptions as gateways to spirit worlds. Across cultures, cold has been used as a medium to push the mind beyond its normal boundaries, much as physics uses it to push matter into novel states. Every step toward lower temperatures carries with it consequences that remain incompletely understood. Superconductors may revolutionize energy transmission, yet they are fragile, collapsing back to resistance when temperatures rise. Superfluids exhibit uncanny properties that defy intuition, yet their coherence vanishes when warmed. Bose-Einstein condensates last only moments before decohering. The universe permits glimpses, but not permanence. Cold reveals possibilities, but also imposes strict temporal limits. In space, where sunlight cannot reach, similar processes unfold on scales that dwarf laboratory equipment. The vacuum itself, seemingly uniform, harbors gradients of temperature shaped by radiation, expansion, and shielding. The cosmic microwave background provides the universal floor of 2.7 Kelvin, Yet localized processes can drive matter lower. Cold is sculpted not by design, but by entropy, expansion, and isolation. And it is in these environments, far beyond human reach, that matter reveals how close it can approach the silent horizon of absolute zero. The further one traces the implications of these limits, the more apparent it becomes that cold is not simply a number on a scale, but a condition with the power to alter states of both matter and mind. And yet, the regions where it manifests most dramatically remain rare, hidden, and fragile, poised in ways that defy ordinary comprehension.
The very fabric of space itself offers an immense stage for cold to dominate. Unlike the surface of Earth, where sunlight, atmosphere, and geothermal activity create constant fluctuations, interstellar and intergalactic space operate under conditions almost entirely stripped of warmth. Between stars, the medium is not empty but filled with tenuous gas and dust, dispersed across distances so vast that collisions among particles are rare. Without frequent interactions to generate heat, these regions sink to temperatures perilously close to the baseline set by the cosmos itself. That baseline is determined by the cosmic microwave background radiation, the lingering afterglow of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson through the persistent hiss in their radio antenna, it represents the cooled remnant of the universe's primordial fireball. Once, this radiation blazed at thousands of degrees. Today, after billions of years of expansion, its spectrum corresponds to a temperature of about 2.725 Kelvin. It provides a uniform thermal bath, bathing every galaxy, every atom, in a faint microwave glow. No matter how far from stars or galaxies one travels, this radiation persists as the minimum environmental energy. Yet this minimum is deceptive. The emptiness of space means that matter can reach equilibrium with this background only over immense timescales. Local conditions alter the balance. A grain of dust shielded deep within a molecular cloud may radiate away heat more quickly than it can absorb it, slipping beneath the expected average. A gas expanding outward from a dying star may, under the right conditions, outpace the inflow of cosmic radiation, dropping to temperatures so low they seem paradoxical. In space, cold is sculpted by the absence of interaction, by expansion, isolation, and shielding from light. The Moon provides a stark illustration of how environment dictates temperature. Its surface, exposed directly to the Sun without atmospheric protection, can rise to over 120 degrees Celsius during the lunar day. Yet in craters near the poles, where sunlight never penetrates, temperatures have been measured below 40 Kelvin. Mercury, closer to the Sun, harbors similar craters that plunge into comparable extremes. These reservoirs of cold are not cosmic averages but geographical accidents, where geometry and absence of atmosphere conspire to create stillness. They remind us that extreme cold need not exist only at interstellar distances. It can manifest even within our solar system under the right constraints. On a grander scale, dark nebulae illustrate how cold preserves structure across millions of years. These dense clouds of gas and dust block visible light, appearing as shadows against the brighter backdrop of stars. Within them, temperatures hover around 10 to 20 Kelvin, sufficient to slow molecular motion and allow complex chemistry to unfold on icy dust grains. Here, hydrogen bonds with carbon, oxygen, and nitrogen, creating precursors to organic molecules. Cold, far from being a sterile absence, acts as an incubator for complexity. Without it, fragile molecular chains would be torn apart by heat or radiation. The very origins of biology may be entangled with the silence of these frozen nurseries. The human mind grapples uneasily with these temperatures because they resist metaphor grounded in experience. We know the pain of sub-zero winters, the sting of wind that bites exposed skin. But space is colder by hundreds of degrees beyond comprehension. At such temperatures, even nitrogen and oxygen, the gases we breathe, would solidify into brittle ices. the imagination falters, and myth rushes to fill the gap. In Greek cosmology, primordial chaos was followed by Erebus and Nyx, darkness and night, domains as void of warmth as they were of light. In Tibetan Buddhism, descriptions of hell realms include icy plains where beings wander in numb confusion, frozen not only in body but in perception. Across cultures, the coldest states are consistently depicted as alien to human continuity, evoking not fiery torment but the extinguishing of motion itself. Scientific measurement in these regions requires instruments designed to detect the faintest whispers of energy. Infrared telescopes, cooled by liquid helium, extend sensitivity into bands where cold objects shine most clearly. Radio telescopes collect the stretched-out wavelengths that cold gas clouds emit. These technologies mirror the subject they study. Instruments must themselves be cooled, stripped of thermal noise, made nearly as silent as the objects they seek to observe. The pursuit of cosmic cold is not only intellectual but technical, demanding that our machines learn to mimic the stillness of the universe. The psychological dimension emerges again when considering how humans react to the concept of absolute stillness. Cold creates not only physical deprivation but cognitive unease. Experiments in sensory deprivation tanks, while not cryogenic, reveal how the removal of stimulation induces hallucinations, distortions of time, and fragmented self-awareness. Extreme cold in the environment creates similar deprivation. As nerve conduction slows, the brain is fed increasingly impoverished signals. A kind of enforced silence spreads through perception, leading to altered states of consciousness. In cosmic cold, stripped even of radiation, matter itself undergoes an analogous silence, its signals dwindling until only the faint murmur of quantum mechanics remains. The universe, vast and largely inhospitable, carries within it these chambers of stillness where temperature plummets near the theoretical floor. They are not rare anomalies but integral features of cosmic architecture, shaping star formation, molecule survival, and the dynamics of radiation itself. Yet each discovery of a colder region raises a question that resists resolution. If space can harbor temperatures below the universal background, what unseen processes might lie deeper still, concealed in shadows where ordinary measurement falters? Amid the many regions of low temperature scattered throughout the universe, one stands apart with an extremity that challenges both intuition and physical expectation. The Boomerang Nebula, a faint object some 5,000 light-years away in the constellation Centaurus, is not easily visible to the naked eye or even to standard optical telescopes. Its discovery depended on radio and sub-millimeter observations, where the glow of cold molecules betrays their presence. What astronomers found there startled them. Gas chilled to just 1 degree above absolute zero, a temperature even lower than the cosmic microwave background. The source of this phenomenon is a dying star, expelling its outer layers into space with extraordinary velocity. Unlike stars in the earlier stages of their lives, which fuse hydrogen and radiate steady warmth, this object is in decline, shedding mass at a rate that destabilizes its internal balance. The expelled material, expanding rapidly, undergoes adiabatic cooling, the same principle by which air rushing through a nozzle or gas decompressing in a vacuum drops in temperature. In ordinary conditions, such cooling is limited by the surrounding environment, which reheats the gas toward equilibrium. But in the Boomerang Nebula, expansion has been so violent and isolation so extreme that the material has fallen beneath the universal background level. The structure of the nebula, imaged in greater detail by the Atacama Large Millimeter/Submillimeter Array, resembles twin lobes of gas fanning outward, reminiscent of a bow tie or a distorted hourglass. Within these lobes, carbon monoxide molecules radiate faintly, allowing their temperature to be inferred. That radiation is not simply weak. It indicates a thermal condition approaching the deepest physical limit. To compare, liquid helium, one of the coldest substances achievable on Earth without elaborate intervention, liquefies at 4 Kelvin and only reaches superfluidity below 2.17 Kelvin. The Boomerang Nebula's core falls beneath both thresholds, placing it in a regime no terrestrial cryogenics can naturally replicate. From a physical standpoint, this extraordinary chill is not permanent. Over tens of thousands of years, radiation from surrounding space will gradually warm the expelled gases. But in cosmic terms, the timescale is long enough to preserve a record of processes rarely observable. A dying star has created an accidental cryostat, a natural laboratory where molecules drift in near-frozen suspension and where chemistry slows to a crawl. In this pause, scientists glimpse the way cold can sculpt matter into forms alien to terrestrial familiarity. The mind struggles to picture such an environment. It is not the sparkling frost of polar landscapes or the blue sheen of glaciers. It is an emptiness devoid of texture, where even the notion of surface loses meaning. Matter in this state does not glisten. It recedes into near invisibility, emitting so little energy that detection itself requires instruments stripped of their own thermal noise. What emerges on the screen of a radio telescope is less an image than a trace, a whisper from a realm of stillness that mocks human scales of perception. Yet this remoteness is not without human resonance. Cold, in psychological terms, has always symbolized withdrawal, distance, or death. Cultures across the globe have equated breath's disappearance with the onset of chill, the cooling of flesh marking the transition from life to absence. In the Boomerang Nebula, the dying star mirrors that association. As its internal fires falter, it expels not warmth but an expanding shroud of cold, a final gesture of silence written across light years. The parallel is not poetic invention, but a recognition of how physical processes align with archetypal meaning. The star at the heart of this nebula is itself no longer visible in ordinary light. Hidden behind the thick envelope of dust and gas it has cast off. To peer into its center requires wavelengths capable of slipping through opaque barriers, yet even then, details remain obscure. What is known is that the expulsion is not steady but violent, ejecting material at hundreds of kilometers per second. The sheer speed is crucial, for only such rapid expansion can drag thermal energy downward so effectively. It is a reminder that cold, in this context, is not a passive drift but the product of ferocity. Violence, paradoxically, creates stillness. In a broader astrophysical frame, the Boomerang Nebula illustrates how the late stages of stellar evolution can generate conditions far outside the range of ordinary experience. Planetary nebulae, supernova remnants, and stellar winds all demonstrate the complex interplay of heating and cooling, compression and release. Yet among them, few, if any, exhibit such extremes of temperature. It raises questions about what other hidden environments might exist, veiled behind dust or located at distances where current instruments cannot yet probe. If one dying star can produce the coldest known object in the universe, what other anomalies might linger unrecorded in the unseen reaches of space? Each refinement in observation uncovers new layers. Infrared detectors trace faint warmth, while millimeter arrays reconstruct flows invisible in optical light. But the deeper scientists peer, the more elusive the image becomes. Cold does not reveal itself readily. It resists illumination, offering only minimal radiation, always threatening to disappear into the background. To confront such resistance is to recognize that the universe retains secrets hidden not in blinding brightness, but in absence, in the near-total erasure of energy. The Boomerang Nebula, fragile in its isolation, continues to expand into the void. Its temperature, for now, remains the lowest ever recorded beyond laboratory walls. Yet expansion is ongoing, and with it, the conditions that sustain this cryogenic state will evolve. Whether colder environments lie undiscovered, or whether this nebula represents a limit yet unmatched, is not known. But the principle it demonstrates, that cosmic processes can carve out states rivaling the most advanced achievements of human physics, ensures that the search cannot be confined to what is already visible. The extraordinary chill of the Boomerang Nebula is not an accident of circumstance, but the direct outcome of physical processes that unfold when a star nears the exhaustion of its fuel. At its core, the star is no longer stable enough to maintain equilibrium between the inward force of gravity and the outward pressure of fusion. As this balance fails, the outer layers are expelled with immense violence. Unlike the gentle puff of gas that might emerge from a cooler star's final stages, the ejection here is accelerated to a degree that strips away thermal energy faster than it can be replenished. The gas is flung outward at hundreds of thousands of kilometers per hour, undergoing rapid decompression. The principle behind this phenomenon is familiar in terrestrial science: adiabatic expansion. When a gas expands without exchanging heat with its environment, its internal energy spreads across a larger volume, leading to a precipitous drop in temperature. On Earth, the release of compressed air from a tank cools noticeably for the same reason, though the effect is mild compared to the interstellar scale. In the case of the Boomerang Nebula, the velocity of expansion magnifies the cooling to extremes. The gas races away from the star so quickly that it outruns the inflow of the cosmic microwave background, shedding energy faster than ambient radiation can restore it. This cooling is not uniform. Observations suggest that the densest portions of the outflow, concentrated along the central axis of the nebula, have dropped closest to absolute zero. Surrounding shells retain slightly higher temperatures, creating a stratification of coldness that extends across thousands of astronomical units. The structure is not static but dynamic, with turbulence, eddies, and knots forming as gas encounters resistance from previous layers. Each perturbation leaves its signature on the temperature profile, creating regions where cooling is more or less efficient. From a chemical standpoint, this expansion has dramatic consequences. Molecules that would normally be broken apart by radiation survive in these frigid lobes. Carbon monoxide, a fragile molecule in warmer environments, persists here in abundance, radiating faintly in millimeter wavelengths. Water ice and other volatiles condense on dust grains, forming reservoirs of frozen material that may drift intact for eons. Cold preserves what heat would destroy, halting reactions and locking atoms into configurations that remain unchanged across cosmic timescales. The psychological parallel is striking. Just as the nebula preserves fragile molecules, extreme cold in the human brain can preserve tissue in states that defy ordinary decay. Medical research into therapeutic hypothermia demonstrates how lowering body temperature can protect neural cells after trauma, reducing metabolic demand and slowing destructive cascades. Patients placed in controlled hypothermia after cardiac arrest sometimes retain functions that would otherwise have been lost. In this sense, both cosmic and biological systems reveal that cold is not merely absence but a protective stasis, a condition in which time itself seems slowed. Yet cold also erases. In the nebula, expansion has stripped the dying star of its outer layers, reducing it to obscurity behind the curtain of its own making. In humans, prolonged hypothermia leads to the gradual silencing of synapses, the fading of consciousness, and the eventual cessation of self-awareness. Cold preserves, but it also diminishes, turning motion and sensation into something attenuated, ambiguous, and fragile. The ambiguity mirrors the nebula itself. Is the boomerang a monument to survival, preserving matter in stillness, or is it a signal of collapse, a star's violent outbreath freezing itself into obscurity? Astrophysicists continue to debate the peculiar violence of this event. Why did the star eject its material with such force? Some propose that the presence of a binary companion could have triggered instability, the gravitational tug amplifying outflow into jets. Others suggest internal pulsations driven by late-stage nuclear reactions, forcing mass outward in catastrophic bursts. Whatever the mechanism, it transformed an ordinary stellar death into an unprecedented cryogenic display. The mystery remains unresolved, leaving open questions about whether other stars might undergo similar processes unseen across the galaxy. Instrumental challenges amplify the enigma. Detecting temperatures so low requires passing signals on the threshold of noise. Radio emissions from molecules provide indirect evidence, but they are faint, absorbed easily by dust or drowned in interference. Each refinement in telescope sensitivity edges closer to clarity, but even now the measurements remain provisional, awaiting higher resolution or more powerful instruments. The nebula resists complete disclosure, remaining a half-seen enigma rather than a fully charted object. This resistance to clarity resonates with the psychological dimensions of cold as well. The human mind under extreme chill enters liminal states where perception fractures. Time dilates, memory fragments, hallucinations intrude. Explorers stranded in polar regions have recorded moments of profound unreality, as though the boundary between waking consciousness and dream had dissolved. In the Boomerang Nebula, matter itself undergoes a comparable dissolution, shedding not only energy but coherence, expanding into forms that resist ordinary categorization. The deeper this phenomenon is studied, the more it challenges the assumption that the cosmic microwave background sets an inescapable minimum for temperature. That assumption held for decades. The background was thought to impose a universal floor beneath which nothing could cool. Yet the Boomerang Nebula demonstrates otherwise, creating a natural exception where expansion defeats radiation. This single case opens unsettling possibilities. If one star can expel matter into such extremes, might others, hidden in dust or distance, have done the same? What structures of unimaginable stillness might exist beyond detection, colder than anything yet measured, awaiting instruments sensitive enough to find them? While the Boomerang Nebula remains the most extreme case, it does not stand alone in demonstrating how the cosmos carves out regions of cold through unusual geometry and physical isolation. Across the solar system and throughout the galaxy, there exist pockets where energy is so thoroughly excluded that temperatures sink toward the abyss of absolute zero. These cold traps, as planetary scientists often describe them, illustrate how environment and shielding can create frozen sanctuaries that last for billions of years. On the Moon, the absence of an atmosphere ensures that temperature is dictated directly by sunlight and shadow. Surfaces exposed to the sun's rays during the 2-week lunar day heat to blistering levels, surpassing 120 degrees Celsius. But in polar craters, where the angle of sunlight never allows illumination, temperatures fall dramatically. Instruments aboard NASA's Lunar Reconnaissance Orbiter have measured values near 30 Kelvin, colder than Pluto's surface. Mercury, despite being the closest planet to the Sun, contains similar polar craters shielded by its steep walls. Messenger spacecraft observations revealed temperatures around 50 Kelvin within these shadowed depressions. Such environments are so cold that volatile compounds like water, ammonia, and carbon dioxide become trapped as ices, unable to sublimate even over geological time. These deposits matter for reasons extending beyond planetary geology. They form natural archives, preserving material delivered by comets and asteroids over billions of years. Unlike Earth, where tectonic activity and climate cycles erase ancient records, the Moon and Mercury provide stillness. The cold locks away molecules, suspending them in time. In a sense, these craters function like interplanetary museums, where the chemistry of early solar history remains intact, awaiting retrieval. Moving outward, dark nebulae across the Milky Way reveal another dimension of cold. Unlike the bright emission nebulae, where star formation lights up clouds with ultraviolet radiation, dark nebulae are opaque. Their density blocks starlight, creating shadows against the galactic plane. Within, temperatures stabilize around 10 Kelvin. Despite their obscurity, these nebulae serve as cradles for molecular complexity. Ammonia, formaldehyde, and methanol have been detected inside them, frozen onto dust grains or lingering in gaseous form. Ultraviolet shielding allows fragile bonds to persist. Cold here acts less as an obstacle and more as a catalyst, enabling stepwise assembly of molecules that could later seed planetary systems. The anthropological parallel lies in how humans conceptualize hidden cold spaces. Caves, crypts, and subterranean sanctuaries often maintain steady, low temperatures. Across cultures, these places became sites of initiation, burial, or mystical retreat. They symbolized thresholds between life and death, known and unknown. In the same way, cosmic cold traps function as liminal zones, preserving what cannot survive under ordinary exposure. They invite exploration but resist it, storing secrets in silence. Shadowed craters and molecular clouds are not the only repositories of low temperature. Intergalactic voids, vast expanses between clusters of galaxies, are even colder. These regions, sparsely populated with matter, expand with the universe's acceleration. Radiation there is thin, diluted across unimaginable distances. Though difficult to measure directly, simulations suggest that gas in these voids can drop below 2 Kelvin, barely above the microwave background. In such emptiness, collisions among particles occur so rarely that energy cannot easily circulate. The result is a suspension of motion on cosmic scales, a theater where stillness dominates. In the human nervous system, similar principles unfold when sensory input diminishes. Experiments with sensory deprivation chambers consistently demonstrate how the brain, starved of external stimuli, begins to generate its own illusions. Visual and auditory hallucinations emerge not because of external causes, but because silence itself provokes the brain to fabricate activity. Cosmic voids, in their silence, might be said to mirror this process in physical terms. Deprived of collisions, radiation, and interaction, they drift into a form of stillness that resembles the brain's hallucinatory silence. Both systems remind us that absence can create a different kind of presence. Another remarkable instance of natural cold occurs on comets. Their surfaces, often coated in dark organic material, can plunge to below 50 Kelvin when far from the Sun. Yet beneath their crusts lie ices preserved for billions of years, untouched since the early solar system. When spacecraft like Rosetta approached Comet 67P/Churyumov, Gerasimenko, instruments detected frozen volatiles and complex organics embedded in its nucleus. These materials, locked in cryogenic stasis, represent chemistry that predates Earth itself. Cold here is not incidental. It is the reason these molecules survived across epochs. As astrophysicists refine detection techniques, they uncover even subtler examples. Instruments capable of measuring the faint glow of rotational transitions in molecules have mapped temperatures across galactic filaments, identifying regions where gas never warmed beyond a few degrees Kelvin. In these faint backwaters of structure formation, matter drifts in semi-permanent suspension, waiting for gravitational perturbations to gather it into new stars. Cold, in these places, is not absence but potential, a pause in which future structures incubate unseen. These environments remind us that extreme cold is not uniform across the universe, but emerges wherever shielding, expansion, or isolation prevent energy from accumulating. Each instance adds texture to our understanding of how matter persists and transforms under minimal motion. Yet with every discovery comes another unresolved question. How many such sanctuaries remain unseen, hidden in shadow or distance, harboring conditions that press even closer to absolute stillness? If cosmic cold emerges from expansion and isolation, the laboratories of Earth demonstrate another path toward reaching the lowest temperatures. Deliberate manipulation of atoms using carefully engineered techniques. The natural universe may create cold as a byproduct of dying stars and shadowed craters, but human science forces matter into stillness with precision, reducing its motion beyond what seems intuitively possible. This pursuit, beginning with liquid gases in the early 20th century, has advanced into realms where temperatures are measured not in degrees, but in fractions of billionths of a Kelvin. The earliest breakthroughs involved the liquefaction of gases once thought impossible to condense. James Dewar succeeded in liquefying hydrogen in 1898, and common followed with helium in 1908. These milestones opened the door to cryogenics, allowing scientists to explore temperatures a few degrees above absolute zero. Onnes's subsequent discovery of superconductivity in 1911 demonstrated that matter undergoes dramatic transitions at these extremes, behaving in ways not anticipated by classical physics. Such discoveries reshaped the understanding of temperature itself, revealing it as a gateway to hidden phases rather than merely a measure of warmth or cold. By the late 20th century, advances in atomic physics had made it possible to move beyond liquid gases. Laser cooling, pioneered by Stephen Chu, Claude Cohen-Tanuji, and William Phillips in the 1980s, introduced a radically new method. By directing tuned beams of light at atoms, physicists slowed their motion through repeated photon absorption and emission. Each absorbed photon imparted momentum opposite to the atom's motion, gradually reducing its velocity. With the addition of magnetic fields to trap atoms in place, researchers created environments where temperatures fell to micro-Kelvin levels. These techniques evolved into the creation of Bose-Einstein condensates, predicted in the 1920s by Sachendranath Bose and Albert Einstein, but only realized in 1995. In these condensates, atoms collapse into a single quantum state, behaving collectively as one. The distinction between particle and wave blurs. Coherence spreads across the entire cloud. Matter under these conditions is no longer a collection of individuals, but a unified entity governed by quantum mechanics at macroscopic scale. Such condensates represent states colder than any natural environment in the universe, surpassing even the Boomerang Nebula's extreme. Magnetic and evaporative cooling refine these results further. In evaporative cooling, the most energetic atoms are selectively removed from a trap, leaving behind the colder remainder. Repeated cycles drive temperatures down to nanokelvin levels, where atomic motion is nearly imperceptible. These manipulations reveal that cold is not a static endpoint but a continuum of ever deeper layers, each exposing new phenomena. Superfluid vortices, quantum phase transitions, and fluctuations dictated not by thermal noise but by the uncertainty principle itself. The applications of such states extend beyond curiosity. Superconducting materials, when cooled, enable magnetic levitation, ultrasensitive detectors, and the possibility of lossless power transmission. Superfluids flow without resistance, defying gravity's pull along container walls, suggesting potential for precision gyroscopes and sensors. Bose-Einstein condensates provide testbeds for quantum theories, allowing physicists to probe how coherence, entanglement, and interference operate at scales visible under microscopes. In each case, cold does not end processes but initiates them, carving pathways into regimes where ordinary intuition fails. The psychological resonance of these engineered extremes cannot be overlooked. When humans induce cold states in matter, they mirror practices that have long sought altered states of consciousness through cold exposure. Breath holding in icy water, fasting in wintry landscapes, or immersion beneath freezing waterfalls all suppress ordinary physiological rhythms, pushing the body and mind toward thresholds where perception shifts. Laboratory cooling of atoms produces a similar suppression of ordinary rhythm, stripping away thermal noise until only quantum coherence remains. Both paths, cultural and scientific, converge on the insight that absence of motion can expose realities concealed by excess energy. Experiments have revealed startling analogies. In Bose-Einstein condensates, sound propagates not as ordinary waves but as quantized excitations resembling particles. Physicists have used these systems to simulate black hole horizons, mimicking the conditions under which Hawking radiation might emerge. Cold becomes a tool not merely for reaching lower temperatures but for constructing analog universes, scaled-down versions of phenomena otherwise unreachable. Just as shamans once entered cold-induced trances to glimpse hidden worlds, physicists enter cryogenic laboratories to reveal dimensions inaccessible under warmth. The technical challenges remain immense. Cooling atoms to nanokelvin levels requires elaborate isolation from external vibrations, shielding from stray electromagnetic fields, and equipment that operates at the edge of stability. Any residual heat, even from surrounding instruments, threatens to erase the fragile state. This vulnerability reflects the precariousness of cold itself. It cannot be sustained without constant vigilance. The same fragility applies to human experience of cold. Too little exposure provokes heightened awareness. Too much erases it altogether. The line between revelation and destruction is as narrow in physics as it is in psychology. As laboratories extend their reach, they confront paradoxes of measurement. To observe matter at extreme cold requires tools that do not themselves disturb it. Yet every photon used to probe atoms introduces energy, raising temperature fractionally. Scientists walk a tightrope. To measure is to risk interference, to observe is to alter. In this tension lies a deeper truth about the pursuit of cold. It resists possession, always threatening to slip away at the moment of contact. The march toward colder states continues, each breakthrough suggesting further depths yet unexplored. Techniques involving sympathetic cooling, quantum feedback, and manipulation of individual ions hint at even lower thresholds. Each step requires greater precision, narrower margins, and stricter isolation, approaching a silence that verges on absolute stillness. What lies beyond these thresholds remains uncertain, but the direction points toward conditions where matter behaves less like substance and more like a pattern of probability waiting to be unveiled. The pursuit of extreme cold in the laboratory is not driven only by technical ambition. It stems from the recognition that suppressed motion reveals properties of matter invisible under ordinary conditions. At low temperatures, the boundaries between states blur, and entirely new regimes of physics emerge. These regimes are not abstractions. They offer practical insights into quantum mechanics, condensed matter physics, and the possibility of technologies that could redefine the limits of human capability. One of the most profound revelations of ultracold research has been the confirmation of Bose-Einstein condensation as a macroscopic quantum state. In ordinary matter, atoms behave as independent individuals, colliding and exchanging energy. But at nanokelvin temperatures, large ensembles of atoms collapse into a single wave function. Their individuality dissolves. Coherence extends across the cloud as though it were one organism. Such states allow scientists to visualize quantum mechanics not as a hidden theory of probabilities, but as a directly observable phenomenon. The cold does not strip matter of meaning, but saturates it with order, forcing particles to reveal their deepest nature. Beyond condensates, cold opens pathways to other exotic forms of matter. Fermionic gases, when cooled sufficiently, pair into states that mimic superconductivity, offering insight into how electrons behave in high-temperature superconductors, a problem that has defied explanation for decades. Quantum phase transitions, unlike classical ones such as water freezing into ice, occur not because of thermal energy, but because of shifts in quantum interactions. By cooling atoms until thermal noise disappears, physicists isolate these transitions, mapping out the fundamental architecture of quantum systems. Each observation provides not only confirmation of theory, but a blueprint for future application. Superconductivity itself illustrates why cold is central to technological progress. When electrons in a material pair into Cooper pairs at low temperatures, they move through the lattice without scattering, eliminating electrical resistance. This effect allows currents to flow indefinitely, magnetic fields to levitate objects, and energy to transmit without loss. The implications are enormous. Power grids without wasted heat, maglev trains floating on superconducting tracks, medical imaging machines with unparalleled precision. Yet most superconductors demand cryogenic cooling, binding their promise to the mastery of low temperature. If higher temperature variants can be engineered through insights gained in ultra-cold experiments, the consequences for civilization could be transformative. Superfluidity is another frontier revealed by extreme cold. Liquid helium, when cooled below its lambda point, ceases to behave like an ordinary liquid. It flows without viscosity, climbs container walls, and circulates endlessly in closed loops. In Bose-Einstein condensates, similar behavior arises, producing vortices that persist without dissipation. These properties defy common intuition, yet obey rigorous quantum laws. Studying them illuminates how coherence, entanglement, and symmetry breaking govern reality at its most basic level. The mind's relationship with these phenomena is complex. Cold in the human body suppresses neural activity, slowing conduction velocity in axons, reducing neurotransmitter release, and altering synaptic efficiency. Experiments in cryogenic neuroscience use localized cooling to silence regions of the brain temporarily, allowing researchers to map circuits by observing which functions disappear. These methods reveal how cognition depends on delicate balances of activity and rest, much like matter itself depends on balances of motion and stillness. Cold, applied carefully, discloses structure by erasing noise. Psychological experiments with perception echo these principles. Sensory illusions become more pronounced when the nervous system operates under slowed conduction. Cold-induced numbness alters tactile feedback, creating phantom sensations or misinterpretations of touch. In extreme cases, the deprivation of thermal input leads to disorientation and hallucination, as the brain substitutes absent signals with fabricated ones. These distortions resemble the coherence and interference patterns observed in quantum systems, not because the mind is quantum in operation, but because absence, whether in atoms or neurons, invites pattern to emerge in unexpected forms. Applications of ultra-cold research extend into frontiers once confined to speculation. Quantum computing, for example, requires qubits to remain coherent long enough to perform calculations. Thermal noise is the enemy of coherence, introducing errors and destroying entanglement. Only by cooling systems to near absolute zero can qubits maintain stability. Dilution refrigerators, vast machines designed to reach millikelvin levels, now underpin nearly every experimental quantum computer. The race to control low-temperature physics is not only scientific but geopolitical, tied to the future of computation, cryptography, and artificial intelligence. Astrophysical analogies continue to emerge from laboratory cold. Researchers use condensates to simulate cosmic phenomena impossible to replicate otherwise. By shaping condensates with lasers and magnetic fields, they create analogues of event horizons, black hole radiation, or cosmic inflation. These models allow direct testing of theories that would otherwise remain inaccessible. Cold, paradoxically, becomes the medium through which the hottest and most violent processes in the universe are studied. The fragility of these states underscores a deeper theme. Extreme cold is inherently unstable, always under threat of disruption. A slight fluctuation, an unintended photon, or a stray vibration can collapse a condensate, destroy coherence, or reintroduce resistance. This mirrors the fragility of human consciousness under cold stress, where clarity is replaced by confusion with only a minor drop in temperature. Cold is both a revealer and a destroyer, exposing hidden layers of order while simultaneously eroding the conditions that sustain life. As experiments refine their methods, questions multiply. What new states of matter remain undiscovered in the narrow space between absolute zero and the limits of current technology? Can coherence be sustained long enough to build stable quantum systems, or will fragility impose barriers that cannot be crossed? Is the architecture of the universe itself mirrored in these states, hinting that what happens in the laboratory reflects processes unfolding invisibly across interstellar voids? Each attempt to answer seems to open further uncertainties, drawing science deeper into the paradox of stillness. The implications of mastering extreme cold extend well beyond the laboratory. Space exploration, in particular, is shaped by the physics of low temperatures, both as an obstacle and as an opportunity. Spacecraft must endure environments where components are alternately heated by unfiltered sunlight and chilled by shadow to below 100 Kelvin. The design of instruments, power systems, and protective shielding depends on understanding how materials behave when thermal energy is stripped away. Cold is not incidental in space travel. It is a condition that determines whether missions succeed or fail. Sensors capable of detecting faint cosmic signals rely on cooling to suppress their own noise. Infrared telescopes, such as the James Webb Space Telescope, operate with instruments cooled to just a few tens of Kelvin. Without this cryogenic environment, the detectors would drown in the heat they emit themselves, rendering the faint glow of distant galaxies invisible. Earlier missions, like the infrared astronomical satellite in the 1980s, pioneered this approach, carrying tanks of liquid helium to cool their optics. Modern designs use multi-layered sun shields and mechanical cryocoolers, reducing reliance on consumable cryogens. Yet the principle remains unchanged. To hear the whispers of the universe, the instruments must first learn silence through cold. Spacecraft navigation and communication also benefit from insights into low-temperature physics. Superconducting circuits, when cooled, enable magnetometers of unparalleled sensitivity, capable of detecting the faintest traces of planetary fields. Quantum sensors built on ultra-cold atoms promise gyroscopes and accelerometers that can navigate without reliance on GPS signals, an invaluable capacity for deep space missions. Each advancement in controlling extreme cold on Earth prepares the groundwork for systems that may function autonomously across interstellar distances. The human body, however, confronts cold in space as an existential hazard. Without atmospheric protection, exposure to vacuum results in rapid heat loss by radiation and evaporation. Yet it is not instantaneous freezing, as popular imagination suggests, but a sequence of physiological crises: boiling of saliva, hypoxia, circulatory collapse. Cold is one among several lethal factors, though it ensures that no unprotected organism can persist. Even within spacecraft, thermal regulation demands constant energy expenditure. Heating systems counter the surrounding void's chill, while cooling systems prevent equipment and crew from overheating in sunlight. Cold is both absent and omnipresent, shaping the architecture of survival. Future exploration may rely more explicitly on cold as a resource rather than merely an obstacle. The shadowed craters of the Moon and Mercury, with their reservoirs of frozen volatiles, are prime targets for resource extraction. Water ice, preserved at 40 Kelvin, could be harvested for life support, fuel, and construction. Mars, with subsurface ice locked beneath regolith, offers similar prospects. Cold preserves these resources in accessible form, turning what appears hostile into an opportunity for expansion. Yet the logistics of extraction at such temperatures remain unresolved, as machinery must function without seizing or fracturing under the stresses of cryogenic operation. The speculative frontier lies in how ultra-cold physics might shape the future of computation and communication in space. Quantum computers, operating at millikelvin temperatures, already demand elaborate cryostats on Earth. If miniaturized and stabilized, such systems could be deployed aboard spacecraft, enabling real-time processing of data with capabilities beyond classical computation. Quantum communication, reliant on entanglement, is fragile under noise. Maintaining coherence across long distances may only be possible with systems maintained at extreme cold. In this way, the same conditions that define cosmic silence could become the foundation for humanity's most advanced tools of exploration. The psychological and cultural layers of cold extend into these possibilities as well. Deep space travel entails isolation, monotony, and deprivation. Cold has historically been a metaphor for such states, the barren Arctic landscape as an analogue for loneliness, the frozen wasteland as a stage for existential struggle. Astronauts may confront similar associations when journeying into the void. The silence of cosmic cold will not merely be physical but experiential, pressing on the mind as heavily as on instruments. Research into altered states induced by cold exposure may therefore acquire new relevance, offering ways to prepare humans for the cognitive distortions of prolonged spaceflight. One avenue of speculation is cryogenic preservation of human life. While science has not yet achieved reversible cryostasis for complex organisms, research into vitrification and hypothermic suspension continues. Lowering temperature slows metabolism and cellular decay, potentially extending survival during medical crises or long journeys. If perfected, such techniques could transform not only medicine but exploration itself, allowing crews to endure journeys lasting decades by sleeping through them in induced stasis. The obstacles are formidable. Ice crystal formation destroys cellular integrity, and rewarming introduces new stresses. Yet the appeal persists, fueled by the same logic that drives physics to probe ever colder realms. Cold slows time, offering a way to stretch life across distances otherwise unreachable. The deeper one considers these possibilities, the clearer it becomes that cold is not a uniform condition but a landscape of thresholds. Each threshold opens access to states of matter, forms of technology, or dimensions of perception previously concealed. Cosmic cold, laboratory cold, and physiological cold intersect in ways that hint at both peril and promise. The silence of low temperature conceals not emptiness but an intricate architecture, awaiting those willing to venture into its stillness. The trajectory of exploration, whether cosmic or human, seems increasingly bound to the ability to endure, exploit, and understand extreme cold. Yet each advance raises unresolved questions about what lies beyond current thresholds, what new states remain undiscovered, and whether human ingenuity can adapt to environments where even atoms hesitate to move. The existence of regions colder than the cosmic background demonstrates that the universe is still capable of revealing conditions that exceed prior expectation. The Boomerang Nebula, the shadowed craters, the interstellar voids, and the laboratory experiments on Earth all converge on a single point. Cold is not an absence but an active threshold. It shapes matter, dictates behavior, and alters the trajectory of both stars and minds. The coldest known place in the cosmos is less a destination than a reminder that nature is governed by laws that admit extremes beyond intuition. The legacy of such discoveries is more than technical. They alter how humanity conceives of its place in the cosmos. For millennia, cold was a seasonal hazard, a climate to endure, or a metaphor for death. Only in recent centuries has it become a scientific frontier. Each step downward on the Kelvin scale has not merely expanded physics, but also deepened cultural imagination, transforming cold from obstacle into instrument. Where ancient myths saw frozen wastelands as realms of punishment or silence, modern science sees them as laboratories of coherence, order, and hidden potential. Yet these insights are inseparable from fragility. A star can create the coldest known environment only by expelling its life into space, an act of collapse that strips it bare. Laboratories maintain their condensates only through constant vigilance, a slight disturbance destroying coherence. Human bodies walk a line between revelation and death when exposed to cold, discovering clarity only until hypothermia silences awareness. Fragility is the cost of revelation. The colder the state, the less stable it becomes, resisting permanence as though secrecy were woven into its fabric. Even so, the consequences reach outward. Superconducting circuits, cryogenic detectors, and quantum computers already depend on cold to suppress disorder. Future exploration of planets and moons will turn to cold reservoirs as sources of water, fuel, and archived chemistry. Medicine continues to test whether controlled cooling can suspend decay or preserve consciousness after trauma. In each domain, cold reveals pathways that warmth cannot, its silence providing structure where noise would otherwise dominate. The coldest known environments remind us that energy is not evenly distributed across the universe, but sculpted by violent expulsions, deep shadows, and relentless expansion. They show that the universe contains not only furnaces of fusion, but also chambers of stillness, each with its own role in the architecture of matter. The tension between heat and cold, motion and stillness, defines the cosmos as surely as gravity or light. To approach one side without the other is to misunderstand the balance. What remains unresolved is whether colder places exist, hidden beyond reach. Instruments improve, but each discovery is conditioned by sensitivity, shielding, and distance. If a nebula can cool beneath the universal background, could other stellar remnants or voids push closer still? If laboratory experiments can approach billionths of a Kelvin, might new methods breach thresholds that now appear absolute? The pursuit is not only scientific but philosophical. How close can anything come to absolute silence, and what lies at the horizon where motion ceases entirely? The mind is drawn to this horizon because it mirrors its own limits. Just as atoms lose individuality in condensates, consciousness under deprivation loses its distinctions, fragmenting or dissolving into illusions. Just as matter preserves fragile molecules in the cold of nebulae, memory itself may linger in altered states induced by hypothermia, extending awareness in ways still imperfectly understood. Cold in physics and cold in psychology are not metaphors borrowed carelessly from one another. They are parallel thresholds where structure is disclosed through suppression, where order emerges when energy falls away. The coldest place in space is not a final record, but a signal. It reveals that the universe is more intricate than warmth alone suggests, that silence carries its own architecture, and that extremes remain to be discovered. What we know is provisional. What we suspect stretches into a spectrum of possibilities shaped by expansion, shielding, and collapse. Each measurement presses against uncertainty, each glimpse into the silence reminding us that the cosmos conceals more than it reveals. And in that concealment lies the unresolved condition that drives exploration. If matter can approach stillness without disappearing, then somewhere beyond the reach of current perception may lie states colder still, waiting in silence for instruments sensitive enough to find them.